Now we come across the Intermediate Value Theorem. Da, da, da. Okay. Detective, fearless teacher, says, at 2 p.m., I noticed that Sam was inside the classroom. At 2:03 p.m., I saw him outside the classroom. When did he leave? Well, we don't know exactly when he left, but we knew that if he was inside at 2 and outside at 2:03, sometime between 2 and 2:03, he had to cross through the door. And this leads us to the Intermediate Value Theorem. Really a very easy concept. Okay, so let's take a graph, and let's take a polynomial function. We're just going to call it f of x. And we know right here is where it's crossing the x-axis. But let's say that we don't really have the graph. So we don't know exactly where it's going through. We know that there's a 0 there somewhere, but we can't even factor it to figure that out. And what we want to know is if we take a point to the left of it on the x-axis and a point to the right on the x-axis, and then examine where the function is at those 2 points as far as f of x goes, you can see that at we have point A, and f of A is less than 0. In other words, the graph is below the x-axis at that point, which means it makes it negative. All right? And at point B, the graph is above the x-axis, so f of b is greater than 0, so it lies above. So what we know is if we let f be a polynomial function with real coefficients, if f of a and f of b have opposite signs, then there is at least one value of c between a and b. We don't know exactly where it is. What we could do is keep moving a and b in closer and closer and closer to each other to try to estimate that. But we do know that between a and b, the graph does cross the x-axis because it was below at A and it's above at B. It's like Sam being inside the classroom at 2 and outside the classroom at 2:03. All right, let's do an example, and you'll be amazed how easy this is. Show that the polynomial has a real 0 between 2 and 3. And here's my polynomial. So what I'm going to do is I'm going to plug in 2 and solve, and I get -1. So I know that at x equals 2, the value of the polynomial is negative. It's below the x-axis. And at 3, it's 26, positive 26, which is above the x-axis. So that means, yes, the signs change. So there is a 0 between 2 and 3. Now, notice I don't care about the 1, and I don't care about the 26. I only care that one of the values is positive and one of the values is negative. All right, so this is going to be a plug and chug type thing. So go ahead and do checkpoint number 8. Turning points. This sounds like ballet now. If I take a look at this graph, and I will tell you that I know that the equation of this graph is x to the 5th minus 6x cubed plus 8x plus 1. And I can take a look here and I see that it is a 5th degree polynomial. The degree is 5. Now if I take a look at how many turns it has, I see it has 4 turns, where it turns around and goes the opposite direction or has a turn. And the number of turns is 4. What is the connection between the 5 and the 4? Well, if f is a polynomial of degree n, then the graph of f has at most n minus 1 turns. So if it's a 7th degree, it would have 6 turns. If it's a 3rd degree, it would have 2 turns. Take a look at this one. We can tell a lot about this. This is f of x equals x cubed plus 3x squared minus x minus 3. And I can see that it is a 3rd degree polynomial. So the number of turns it has is 3 minus 1, which is 2. There you go. And that's all there is to this one. Pretty simple, huh? See you later.